So I'm in RStudio here, which I find practical to run the lavaan software. And so I'm going over here on the right hand side on this to this icon called import data set. I'm going to click on that, and in this case my data set is a text file. Obviously you could have other formats like Excel or SPSS or whatever. So I'm going to import now my data set from a simple text file, and my data file is called sem.txt. You find this data set as part of the supporting materials for this session down below this video, so you can download it and practice yourself with these data. I'm going to open it, and you can see here that in the first row I have the variable names according to the formal notation that I introduced in previous sessions. So I have 6 indicators: y11, y21 measure the first factor, and then y12, y22 measure the second factor, and y13 and y23 measure the third factor in this case. So I'm going to click on heading yes here on the left hand side, so that R will automatically, or RStudio will automatically recognize that the first row here contains the variable names. If you don't have variable names in the data set, then obviously there will be some default names added. Then you would choose the option heading no. So let's click on import, and then we should get our data set on the left hand side to view. You can see here this looks good. We have 6 columns and they are labeled according to our variable names. Now the first 2 indicators here measure the first factor, physical health. I simulated this data set so that it would be in line with our models, so that I can demonstrate, so say, how these models work here. And so I simulated the first 2 indicators to be measures of physical health. Now the next thing I'm going to do is I'm going to open a prepared syntax file so that you can see what that looks like in lavaan. So I'm going to click here on File, Open File, and then I have a syntax here that's called CFA syntax.r. And so you can see that this model can be specified with just a few lines of code. This is one big advantage of lavaan over other software programs for structural equation modeling. It is really straightforward in terms of the syntax. It's pretty self-explanatory, and you can specify models with just a few lines of code. So the first thing here, the first command, just simply calls in that lavaan package, which is already installed here on my computer. If you haven't installed it, then you would have to download and install that lavaan package first. And then the second command defines an object called CFA, and so that's our model, CFA for confirmatory factor analysis. And you can see that the single line here of code, pH equals sign tilde, defines the factor pH, physical health. So pH is that latent variable or factor that we want to measure, and so it's a name or a label that we pick, and then it is measured by the variables y11 and y21 in our data set, where you can see that before the second variable I included 1 times, and that's because both of the factor loadings in this simple one factor model have to be fixed to 1 for it to be identified. Why do I have to write 1 times only in front of or before the second indicator? That is because by default lavaan will constrain the loading of the first indicator to 1 always. So this will always be the case, and the reason is that when we estimate confirmatory factor models with latent variables, then we always have to have one indicator that scales the latent variable. So we need to always be sure that the latent variable has a defined metric, because it's not per se uniquely defined in terms of its units of measurement. And so the default approach to set the scale of the latent variable is to fix the loading of one indicator to one, and that's because that's kind of arbitrary in many situations. Many software programs for SEM just simply pick the first indicator that appears in the code after the equal sign and constrain that loading to 1. Now there are other ways to set the scale of the latent factor. You can also estimate the loadings and fix the factor variance directly. That's an alternative approach, but in many situations fixing the loadings, fixing one loading has an advantage, and that's why many programs do it like that. So this means we don't have to constrain the first loading or include a command for that, because it's already by default constrained to 1. But the second loading would be estimated freely, as well as all other loadings, if we didn't include a statement 1 times. Now, with just 2 indicators, again, we have to fix the loadings. Later on, we will see when we have more indicators, more factors, then that is not necessary. So this is really because this is a tiny model, and in order to get it to be identified, we have to put in this constraint, which makes this model a model of essential tau equivalence according to test theory. Next, we define an object called fit, which includes fitting the CFA model. So this SEM function can be used for both confirmatory factor analysis and SEM with latent variables. And so in this SEM function, we define that our model is this model CFA that we have written out in the previous line of code, that the data set is called SEM. So that's the data set that I called in earlier. The estimator that is used here is maximum likelihood with robust standard errors and test statistics. I chose that to show you that you can fit a model like that even when you have non-normal data. So the MLR estimator is suitable when you have non-normally distributed data that don't meet the assumption of multivariate normality. Then you'll get robust standard errors, robust fit statistics for your model. Furthermore, I also included a command here that is called missing, and that specifies that full information maximum likelihood estimation will be used, which is an option when you have missing data to include all available data. This is, in terms of the mathematical theory, this is equivalent to multiple imputation in terms of its assumptions. And so it's a very convenient way to address missing data when you have a path model, a confirmatory factor model, or a structure equation model. When your data are missing at random or missing completely at random, then you can use full information maximum likelihood estimation, and it will include all your data. So all cases that have partial data will be included without you having to run multiple imputations, and that's a very powerful way to address missing data. And so it's used as the default in many software programs for structural equation modeling, because it yields more appropriate outcomes than listwise deletion when you have missing at random data or missing completely at random data. Furthermore, we have the summary function that allows us to get fit statistics. So here this argument fit measures equals t for true means that we will get a set of model fit statistics that allow us to evaluate a model in terms of how it reproduces the observed covariance and mean structure. And then also we can look at standardized parameter estimates that are of interest oftentimes when we run a factor model or a structural equation model. And we can also get R squared for our observed variables, so that we can look at the reliabilities or the proportion of variance that that is explained by the common factor in each observed variable. And so that's it. So we can then run this syntax to look at the output, which will appear down below. When we scroll down here in our output window below, you can see there's a bunch of output that's been generated now, and you can see that here the estimator is maximum likelihood. In this case, there weren't any missing data, so therefore the number of missing patterns is only 1. There was only complete data. I simulated the data. in this case, but with FIML estimation you could include missing data in the analysis. Then you can see that we get test statistics for model fit, and we get in one column the so-called standard or uncorrected maximum likelihood chi-square test of model fit, and in the next column the scaled version, which is corrected for non-normality, so a scaled chi-square test. The chi-square test tests the null hypothesis that the model fits exactly in the population, meaning that the model implied covariance and mean structure are equal to the population covariance and mean structures. In this case, our model is saturated because we have 5 parameters and 5 pieces of information, and therefore the test of model fit is 0 and the degrees of freedom are 0. So a saturated model is not testable. It must reproduce the observed data perfectly by definition, in the same way as a multiple regression model would reproduce your observed covariances, variances, and means perfectly by definition. Now, this will be different when you have a larger factor model with more indicators and or with more factors. In that case, then the model will be over-identified, and in the next session when we talk about a structural equation model with more factors, then you will see that there will be a non-zero chi-square for such a model that is non-saturated. So we'll see that later. In this case, we can ignore the chi-square here. It doesn't give us any information. You can see that there's also a test statistic, a chi-square statistic for a so-called baseline model. Here, this is the model test for the baseline model. The baseline model is one where it is assumed that in the population there are means and variances of the observed variables that are free to take on any value, but no covariances. So there can be variation in the indicators or inter-individual differences on the observed variables, and they of course can have means, but there cannot be covariances under the baseline model. And so that's a very basic test of whether our model is better than a model that assumes no covariance structure at all, no associations, no linear associations between variables. You can see in this case this model is rejected. It has a very high test statistic, a high chi-square value of over 200, 1 degree of freedom because there's one covariance with 2 indicators, and so that one covariance in this baseline model is constrained to 0, and the hypothesis that this model fits in the population, that this fits perfectly, so say reproduces the data, is rejected because the chi-square is significant. So there's significant misfit between this independence or baseline model and our data, which have a non-zero correlation between the 2 indicators of physical health. So that shows us that it does make sense to model a structure for the covariance between these variables because it's not 0. So that's basically what that baseline model chi-square tells you. The other fit statistics we can ignore for now because our model is saturated, so none of this really is interesting to us. And we'll get to the parameter estimates by scrolling down. You can see that first of all, parameter estimates are given for the latent variables, and so the first thing that we obtain here are the factor loadings. Now you can see under estimate we get the loadings of exactly 1.0 because they're both fixed to 1. So the unstandardized loadings are not interesting in this case because they're both fixed to 1. However, you can see that in the last column, std.all, you get estimates 0.896 and 0.839, and those are the so-called standardized factor loadings, where it is assumed that both the factor and the 2 indicators y11 and y21 are standardized to a variance of 1. So this is of interest because then these loadings give us the correlations, the estimated correlations between each variable and the factor. For example, the first value of 0.896 here gives us the correlation between y11 and pH. So this variable is correlated 0.896 with the factor. The second variable is correlated 0.839 with the factor. And that shows you something, or tells us something about the reliability of each variable, we want to see a strong correlation for reliable indicators. So meaning the stronger the correlation, the less measurement error there is in each of these indicators. And we'll see later that these standardized factor loadings squared give us R squared, or a reliability index in the sense of classical test theory. So these two loadings here are fairly high, showing that these indicators are reliable indicators of physical health. So even though the unstandardized loadings are not interesting and fixed, the standardized loadings are interesting. And so even this saturated model provides some useful information for us if we wanted to learn about the reliabilities of our measurements. Next are the intercepts. In this case, the intercepts or alpha parameters just simply give us the means of the observed variables, so that's not so interesting. And then next are the residual variances for the observed variables. So 0.875 is the estimated residual variance for, or error variance for Y11. 1.503 is the estimated error variance for the second indicator, Y21, and then we get the factor variance for pH, which is estimated to be 3.576. And since these are estimated, they also have standard errors, they have test statistics, z-values, and they have p-values. Now for variances, you wouldn't do a z-test for significance, so that's not appropriate, but you get the estimate for each variance and its standard error to look at. And at the very end, we get the R squared value. So those are the squared standardized loadings that we looked at earlier in the output, and you can see that the R squared for Y11 is 0.803, so 80.3% of the variance in the first measure is accounted for by the factor pH, and so that shows that 80.3% of the variance in the first indicator is true score variance or reliable variance, and only 19.7% of the inter-individual differences on Y11 would be measurement error. So that's good reliability. That's seen as decent for an observed variable. The reliability estimate for the second indicator is a little bit smaller. Here only 70.4% of the variance are estimated to be true score variance. The remaining 29.6% would be error variance. So you can see that even this simple saturated CFA model does provide us with some useful information if our goal is to estimate the reliabilities of our indicators. It allows us to estimate the true score and error variance components and to look at R squared as an estimate of reliability of the indicators.